Alright, so I thought my last video was going to be the last one where I was reviewing material on vector spaces and then would move on to representations. But there's some other stuff about vector spaces I think it'd be good to go over. In particular, some stuff regarding the symmetric product and the exterior product, which I've sort of thought a little bit about more and can give a little more information about. So anyways, before we move on to that, we're going to say another thing about vector spaces and tensor products that I initially skipped over because I wasn't quite sure what the usefulness of this would be. But after thinking about it, because it's not too hard to prove, I figured I'd just go ahead and include it, especially since I want to talk about this stuff anyways. Might as well make another video. So anyways, if you've got two different bases of V, of course V here is finite dimensional, that's why these bases go up to M. And so one of these, we've got VI's here, and here we've got VI tildes. So we've got two bases. Then if you look at this particular element, which is the sum of VI star tensor VI, then it's going to be invariant under the choice of basis. And typically, algebraists seem to not like having to choose a basis. And so things that you can say that do not depend on choice of bases tend to be really nice. Especially because like once you fix a basis, it's sort of like, I don't know. There's some reasons why you would prefer to say things without having to choose a basis. But anyways, so to prove this, let's see here. We want to prove these two things are equal. So call one alpha, call the other one beta. Then what we're going to look at is we're going to look at psi of these elements. And psi here is the map which was defined in the previous theorem that comes from the previous video, so go back and look at that if you want. Basically what it does is psi of some element of, let's see here, where is this going to be? This is going to be in, so if you let W be V and, well, I think in the previous video it was like you had two vector spaces V and W. Here we have V star and V. But anyways, evaluating psi here will give you a map, and when you evaluate it at V, what it is you just take this and evaluate it at V. Well, not quite. Okay, here is where it is. So psi of V, psi of something tensor something else of V is equal to taking this, evaluating at V, and then multiplying by this. So this is what psi is. If you look back in the video, psi was used to define phi, but phi was the domain of phi in the previous theorem is just the direct product of, here it would be the direct product of V star and V, and what we're actually starting from is not the direct product or Cartesian product, but the tensor product, and so that's why we have to use psi instead. Anyways, we just do some computations and it works out. Psi of alpha, you just plug alpha in, and then because of linearity, what this is you can bring the psi inside the sum, and evaluating this sum at V, again by linearity of the space that this lies in, is the same as taking the sum of all of these things separately evaluated at V. And then of course you just use the definition of psi here, and then here you replace V with V. So V here is just some arbitrary element, but we can write it as the sums of AI VI's, where AI's are some scalars, and we can do that since the VI's are a basis. But we can do the same thing with the V tilde i's, but we'd have probably different scalars, and we call them BI's here. So anyways, you plug in V, and then if you look at what happens, VI star is going to be delta ij. So at any particular I, this is only going to pick up the j terms. And when you have the j, you're going to get this the scalar a. So at I, it's only going to pick up the I term in this sum. And so you're going to get an AI out of it, and then the VI star of VI is just going to be 1. And so you're going to get an AI from here, and then you're multiplying by that VI again. And so you get the sum AI VI, but that's exactly V. And so now we can replace it with the sum of the BI V tilde I, and just go do the same exact steps that we did before, but do them backwards. And that will give us back to psi beta of V. So psi alpha V is equal to psi beta V, and that holds for all V in capital V, and therefore psi alpha and psi beta define the same linear map. But we also know, we proved last time, that psi is a bijection. Or, technically we proved that phi was a bijection, but the same thing holds for psi. It's just that psi is on the tensor product space. But anyways, so because V is finite dimensional, the previous theorem actually gives us bijectivity, and so we get that alpha equals beta. Because bijectivity implies surjectivity, so if psi maps these two things to the same place, then you must have started from the same place. Oh, well, wait a minute. That actually, I don't think that actually uses that second part where we had finite dimensionalness. Of course, you need to have finite dimensionalness to do this whole other argument, because all of this stuff was using particular bases of two particular bases of V, and we needed all of these sums to be finite because you can't do linearity over countable sums. So really this is injectivity. And injectivity of psi. Okay, so there you go. Alpha is beta. So I guess that's nice. I don't know if we're going to use this for anything. It might just be an interesting result in and of itself, which, I mean, if you think it's interesting, then great. But anyways, let's move on to talking about the symmetric and exterior or alternating products. So remember, what the symmetric product is you take V tensor product with itself k times, and then you mod out by the span of the collection of all vectors that look like this. You take V1 tensor V2 all the way up through Vk, and then you subtract the same element, but you flip two of the indices on the inside, two of the adjacent indices. So if you have any I between 1 and k minus 1, you flip the I and the I plus 1 index, and that's what this thing is. And so of course V1 through Vk, those are all elements of V. And what happens when you span by this is, when you look at this quotient space, if you take an element and you flip any two of its adjacent entries, then those two things are going to be the same, because if you take an element alpha in this space and you write alpha as a tensor product of V1 through Vk, and then you flip Vi and Vi plus 1 for some I and call that element beta, then alpha minus beta equals 0. And so quotienting by this space means that alpha equals beta in this quotient space. And we'll talk a little bit more about that later. That's why you can write elements of the symmetric product as just V1 through Vk, in which order does not matter. And the reason order doesn't matter is because you can flop any of them around and it doesn't change the element, because that is guaranteed by this quotient. Whereas for the alternating or exterior product, you quotient by the span of this plus this, the same thing, but instead of a minus, you have a plus. And so what happens in this space is that if you have an element alpha, which is v1 tensor all the way through vk, and then you flop two of its indices, say you flop I and I plus 1, and you call this new element beta, then how are alpha and beta going to be related? Well, what this says is that because it's in this quotient space, alpha plus beta is going to be equal to 0. So alpha is equal to minus beta. And so what happens when you flip two things is that the sign changes. And so that's I think that's where you get the name alternating from, because it's sort of like with alternating permutation or transpositions in the alternating group, where if you flip them, the sign changes. Oh, no, that doesn't really make sense. If you flip two indices in a permutation, then you're multiplying by a transposition, and so the sign of the permutation changes. Okay, so anyways, that's these things. So we use the conventions. When k is 0, then both these things are going to be just complex numbers. When k is 1, you're just going to have the space k, and that sort of makes sense because these quotients don't really make sense at all. Because then when k is 1, it's a little more obvious that this should be the case, because v to the tensor 1 is just going to be v, and then quotienting by the span of this space, well, here what you're getting is you're just getting the span of 0. At least here you're getting the span of 0. Here you're getting... Yeah, it's just a convention. I'm not going to worry too much about why it should be the case. Anyway, so like I discussed earlier, terms... so if you have an element of sim kv, and you look at its elements are going to be linear combinations of elements of this form. So any element in here, when I say the span, I mean just like linear, like C-linear combinations of these things. And so if you look at any particular element in here, because of this quotient, the order of the VI's doesn't matter, so you can just line them up. And so it's just going to be some VI, V1 through VK, where V1 through VK are just some elements of V. And yeah, so arbitrary elements of this group are going to be linear combinations of these things. Order does not matter because of the quotient. In the exterior product, we have linear combinations of these things, and we use this wedge product here for some reason I'm not quite sure. By the way, this is capital lambda. This is a wedge product. So when I write them, they look the same, but they're not the same. So we have V1 wedge product through VK. Order does matter because swapping any two adjacent things here flips the sign, and so if you permute a whole bunch of these, then you're probably changing the sign to some degree. I guess you might not be, but you don't like. I guess for more details, we'll get down to this equation and discuss it there. But anyways, if you have this wedge product and Vi equals Vj for some I which is not equal to j, then let's think about what happens here. What you can do is you can flop a whole bunch of adjacent things around so that you get the Vi and the Vj next to each other. So it'll be like Vi or V1 wedge all the way up through wedge Vi, wedge Vj, wedge all the way up to wedge Vk. And once you've flip things around so that you get it into that form. You may have changed the sign, but it doesn't really matter, because what you can do there is once you have this element, you know that if you flip the VI and the VJ, then it flops a sign. However, since flopping VI and VJ, since VI equals VJ, flopping those two doesn't change the element. And so what that tells you is that the element is equal to -1 times the element. And that only happens for the 0 element. And so if VI equals VJ for some two different indices I and j, then the whole thing must be 0. Okay, so that's that. And then this should be a bit self-explanatory, that if you take a permutation, then if you start with V1 wedge through VK and you flip them around so that you end up at V sigma 1 through V sigma k, then the sign of sigma will tell you how many different adjacent elements you had to flip in order to get there. And so you're going to have to multiply by the sign of sigma. Okay. Lastly, we'll talk about basis elements. If you have a basis VI for V, then we have a basis of the symmetric product given by V1R1 through VMRM. And that is because, so each of these R1 through Rm is going to be greater than or equal to 0. And their sum is going to be K. So that's because we've got, so if you take an element of this tensor product space, then you're going to get some VIs from each different coordinate. And well, let's see here. You can only really get one from each coordinate. Well, I'm trying to think of a really good, precise way to say why this makes sense. Certainly all these R1 through Rm's need to be greater than or equal to 0, and they need to be less than or equal to K in order for this sum to equal K. And so really what you're doing is you're taking a particular VI from each coordinate. Each coordinate you can pretty much plug in V1 through VK, and the order doesn't matter, and so I think those two things combined should give you this formula. The fact that you basically from each copy of V in this symmetric product, you will take one basis vector between V1 and Vm, and so when you put them all together, you're going to have V1 through Vm. Each of these are raised to some powers, but because you got a particular VI from each index, the powers all have to add up to K. Okay, so that's a basis for the symmetric product. For the exterior product, we know that the terms are linear combinations of elements that look like this, and the order does matter. So you can basically just take any possible indices between 1 and m, right, because our basis has m elements in it. So you take some collection of indices between 1 and m. All of these indices are distinct, because if they aren't all distinct, then it's a 0 vector, and that's not going to be part of our basis. And so yeah, that the indices between 1 and m that you choose are going to determine this vector. And so that gives you a basis for the exterior product. All right, so now this covers pretty much everything that we need in terms of background on vector spaces. And now I promise in the next video we're going to talk about representation theory.